So now we come to our two most important measurements of concentration, molarity and molality. And both of these are reliant on, instead of just any random quantity of solute, these are both very specific to being moles of solute. So molarity, which we abbreviate with capital M, is the moles of the solute divided by the liters, and we have to be very careful about this part. It's the liters of the solution, so not the liters of the solvent. Those are two different things. And it turns out this is so important that we have special glassware just for doing these kinds of things. So this is known as a volumetric flask. And this is what you would use to make a solution of a given molarity. So you can see that this one is 10 milliliters. And they make these in many different sizes. And you may or may not be able to make out, but at the very bottom it says plus or minus 0.025 milliliters. So in other words, this volumetric flask is accurate to within 2.5 thousandths of a milliliter. I'm sorry, 25 thousandths of a milliliter, or 2.5 hundredths of a milliliter. Now, the negative of a volumetric flask is it can only be used to measure one thing, and that's the volume that's listed. So this line right here that you find in a volumetric flask, that line represents that number of milliliters. So you can't use it to measure more than 10 or less than 10. But what you do with a volumetric flask is you add your solute to it, and then you add your solvent up to this line and get everything dissolved. And if the level of solvent has gone below the line, then you add more to come back up to the line. Then you know you have exactly 10 milliliters of solution, or 100 milliliters, or whatever the size of your volumetric flask is. But other than that, these calculations end up being pretty basic, because the liters of solution is something you would measure, and then the moles of solute is something we already know how to calculate. So let's do an example. So we're going to calculate the molarity of 21 grams of sodium chloride in a 1 liter solution. So we need first, on the denominator we put the volume of the solution, which is given as 1 liter. In the numerator though, we need the moles of the solute. So we'll have to take our 21 grams and first convert that to moles. After we do that, we can calculate the molarity as 0.36 molar. Now, very similar to molarity is molality. Molality, which we don't really have much of an abbreviation for, it's usually abbreviated as molal, is again moles of solute in the numerator. But in the denominator, we get kilograms of the solvent. So why the difference? Well, first of all, for dilute solutions, specifically dilute aqueous solutions, molarity and molality are usually extremely similar, if not equal. But what happens as we change temperature? So for molality, molality is temperature independent. So no matter what we do to a solution, the molality doesn't change at all. And that's because moles is mass dependent, and mass itself are both independent of temperature. But what about molarity? For molarity, in most cases, as the temperature increases, volume increases, and therefore molarity decreases. Now, this is something we might not think about, that the volume changes as temperature changes, but it's something we see on pretty much an everyday basis. And turns out it actually has even more important consequences than that. So if you think about water, as temperature changes, the density of water changes as well. How do we know that? Well, probably the easiest way we know that is with ice. We know that ice floats, therefore ice has to be less dense than water. But you can even see, for example, and this chart is extremely detailed. This comes from the CRC Handbook of Chemistry and Physics. Is as our temperature changes. So the way this table is made, this box is 15.0, 15.1, 15.2, and so on. Now, is there a huge change in the density? No, not really. You can see between 15 degrees and 30 degrees, we go from 0.999 to 0.995. So not a huge change. But if you're working with a large enough volume, then this could have a pretty big impact. And once you get up to close to boiling, the density actually goes down as low as maybe 0.96, 0.965, and the grams per milliliter. But it turns out this has even more interesting consequences. In fact, you could make an argument that if ice was more dense than water, that none of us would be here. Can anyone think of a good reason why that's true? Well, let's think about evolution. Where did evolution begin? We know that most life originated in the water. Well, in the winter, if sources of water freeze over, the ice stays at the top and protects what's below with the layer of ice. But what if ice was more dense than water? Well, if ice was more dense, then the ice would actually sink to the bottom of the lake, and then the top would freeze again, and eventually you might be able to get the entire lake to freeze solid, and that would of course kill any life inside. Alright, so let's put all this together and do a little bit more practice. Alright, so we have a solution that's made up of 571.6 grams of sulfuric acid per liter of water. And what I want you to find are the mass percentage, the mole percentage, the molarity, and the molality. So initially it might not seem like we have enough information to do this, but let's see what happens. So mass percent is equal to the mass of solute over the mass of solution times 100. Now we haven't defined an amount of solution here, but that's okay because we can just pick anything because we're given a ratio 571.6 per 1 liter. So let's make it easy. Let's pick 1 liter. So 1 liter of solution, 571.6 grams of sulfuric acid. So we know our mass of solute, it's 571.6 grams. What's the mass of the solution? Well, we know the density, and so 1 liter is 1,000 milliliters times 1.329 grams per milliliter equals 1,329 grams. And so we get a mass percentage here of 43.01%. All right, so we got that one figured out. What about mole fraction? So this is going to be the moles of solute over total moles. So total moles here would be the moles of solute plus moles of solvent. So we can easily calculate the moles of sulfuric acid. Again, we're going to deal with that same 1 liter. So we have 571.6 grams times 1 mole over the molar mass of sulfuric acid. And the molar mass of sulfuric acid is 98 grams. And so that's equal to 5.827 moles. Now, how many moles of water do we have? Well, recall on the last page, we said that 1 liter of solution weighed 1,329 grams. Of that, 571.6 grams was sulfuric acid. So given that the only other thing present is the solvent, which is water, then the remaining amount, which is 757.4 grams, has to be water. And so we can use that with its molar mass to find that we have 42 moles of water. So now finally we can calculate our mole fraction for the sulfuric acid. And that's equal to the 5.827 moles of the solute divided by the total number of moles, so that 5.827 plus 42. We get 0.122. Notice this is a mole fraction, so the answer should be between 0 and 1. It's not a mole percent. All right, the molarity may be the easiest one so far. This is moles of solute over liters of solution. Well, we've already done all the work here, right? We know that if we're dealing with 1 liter of solution, then we just calculated on the last slide that that would be 5.827 moles. And so we get 5.827 molar. Finally, molality. Again, we've already calculated the concentration or the number of moles of the solute in 1 liter. What's going to be very different here is the mass of the solvent. The mass of the solvent here, 0.7574 kilograms of water. Where does that number come from? Well, if we go back here, remember we said if we had 1 liter, then that meant it had a mass of 1329 grams. We subtracted out the 571.6 grams of sulfuric acid to find out the amount of water. Then I just converted it from grams to kilograms. And so the molality here is 7.69 molal. So we said before if the solution was dilute that the molarity and molality would be similar. Here in this case, this is definitely not a dilute solution, and so these numbers are not at all similar. All right, the final piece of this that we need is to talk about dilutions. So this is something we have to do very commonly. So hydrochloric acid, for example, we often purchase it as a 12 molar solution. But we often need to use it in much lower concentrations. So how can we calculate what we would need for, say, a 1 molar solution? So let's say we wanted to make 1 liter of a 1 molar solution. How much of the 12 molar solution do we need? Well, what we need, we're going to keep the same number of moles constant. And so we find if we take our initial molarity times our initial volume, that will be equal to the new molarity that we need times the new volume. So here we want to make a 1 molar solution and we want 1 liter of that. We have a 12 molar solution. What volume do we need? And we can solve that, and we find that X is equal to 0.083 liters or 83 milliliters. So this tells us that we need 83 milliliters of the more concentrated solution to make 1 liter of the 1 molar solution. Again, we can do this because we're not changing the number of moles. So if you think about our molarity equation, molarity equals moles over volume, or moles equals molarity times volume. What we're saying is under these two situations, the number of moles is equal, so we're just setting M1V1 equal to M2V2. It's actually an extremely similar calculation to what we learned with the gas laws. All right, so from here, you're going to want to get some practice dealing with calculating concentrations. So you should bring up and work on in-class exercise number 16.